Scalar motion is a change in relative size over time, unlike vector motion, which is an object changing position. We experience scalar motion as gravity, charge, and magnetism, though we don't recognize it as motion. Euler's formula is a shorthand for vector motion, expressing a point's rotation around the unit circle. The sum of cosine and sine describes its position as the angle changes. Euler's formula transforms linear vector motion into nonlinear vector motion along the unit circle. This works for change of position motion, but not for change of size, or scalar motion, which was unknown to quantum mechanics pioneers. Quantum mechanics pioneers tried to use scalar magnitudes of energy defined by nonlinear vector motion with Euler's formula. When this failed to correlate with discrete energy levels, they turned to Euler-Lagrange points of energy equilibrium and the principle of least action. To address quantum phenomena, theoreticians relied on the mechanics of Newton, Euler, and Lagrange, focusing on vector motion. This approach is complicated, but works well in the lab, though less so in the classroom. Dewey-Larson noted that motion is the only observable relation between space and time, v equals ds dt. He also observed that an object's change of position is assumed from experience and is not found in the equation itself. Larson suggested thinking of motion as a reciprocal space-time relationship, like a double-phased clock. Euler's formula can be adapted to scalar motion, where counterclockwise rotation and increasing angle result in an expanding sine projection and a contracting cosine projection. This is equivalent to using a rotating diameter instead of a radius. Introducing the reciprocal space/time clock. This clock replaces the rotating radius of a familiar clock, with a rotating diameter and its reciprocal. Space and time are inverse aspects of motion. One cannot exist without the other. This view recognizes that space and time must be inverse magnitudes. Motion is defined by both continuous rotation and discrete oscillation. As the diameter rotates, its ends change position, leading to expansion and contraction of the sine and cosine projections over time. Changing the oscillating sine and cosine from vector to scalar motion fundamentally changes both physics and mathematics, resulting in the three intrinsic scalar motions shown here, based on the unit progression. The sine and cosine cycles illustrate expansion and contraction based on the position of the diameter on the clock face, from 0 to 1 and 1 to 0. Opposite reciprocal waveforms are often thought to cancel, but they do not, as they represent two sides of the same phenomenon. Opposites cancel under addition, but reciprocals don't under summation. Based on Larson's scalar motion concept, Douglas Bundy identified three forms of scalar motion: 1D, 2D, and 3D. These correspond to the inverse dimensions of energy, momentum, and mass, leading to a new quantum theory called the Bundy reciprocal system theory, or the BRSt for short, because the theory is based on Larson's new system of theoretical development.